Hi there, this video is going to walk through introducing you to PV work and its relation to the first law. The first thing to keep in mind is that there are a number of different ways that chemical systems can undergo changes. Some of those changes that we'll explore in this class are isothermal processes, which are processes that occur at constant temperature. So that would mean that we have delta T equals 0. Okay, another type of process would be a reversible process in which the pressure changes are in infinitesimal increments. Okay, so for reversible processes, we're thinking about situations where your system can easily kind of find its way back to an equilibrium position. Okay, so for reversible processes, one thing that we can generally say is that the pressure of your system is essentially equal to the external pressure of your system. So for reversible processes, you'll see P is equal to P external. Essentially what that's saying is that basically the pressure of your system is essentially equal to the pressure of your surroundings because the changes are so small. Another type of process we'll encounter is an isochoric process. So that's a process occurring at constant volume. So in that case, we would have delta V equals 0. And we'll also encounter isobaric processes, which are processes that occur at constant pressure. So in that case, delta P would equal 0. And finally, we will also talk about adiabatic processes where there is no heat exchanged with the surroundings. So in that case, we would say Q, our heat, is equal to 0 for an adiabatic process. So the key in working with all of these different types of processes is to really just kind of identify what the situation is telling you. Okay, is it telling you that you have a constant temperature? Is it telling you that you have no heat exchange? Q is 0. Okay, so that is really powerful information that's going to help you to approach your problems and calculations for these different types of situations. All right, so starting out, we're going to focus on what we call PV work. Okay, that's pressure volume work, where you have work that's associated with a volume change. Okay, and that can be calculated using this expression dW equals minus P external dV. Okay, so again, we need to know something about our pressure of our system, okay, and the volume change of our system, and that will give us information about the work involved. We'll use some form of this equation essentially for any type of these calculations that we're going to encounter. So this is really the only equation that you need to commit to memory, and then we'll just kind of play around with what we know about these different situations that will help us get to the correct answer for each one of these situations. There are other ways to do work rather than PV work. Okay, we'll encounter one or two of these along the way this semester. So there's also electrical work, work due to bubble expansion or compression, where we have to take into account surface tension, and also spring stretching or compression. So you can kind of picture stretching a rubber band and the work involved with that. But for now, we're going to focus on our PV work. And just to remind you how work is related to internal energy and kind of the impetus for looking at work to begin with, remember that our internal energy is given by delta U equals Q plus W. Okay, so to say anything about our internal energy, we need to be able to say something about work. So that's why we are taking the time to dive into calculating work for all of these different types of processes. All right, the simplest kind of situation you'll encounter for PV work is that for which work is done against a constant pressure. Okay, so this would be the example of doing a lab experiment that you conduct under atmospheric pressure. Okay, you have that constant external pressure of the atmosphere. So in this case, your external pressure is not going to be affected by any volume changes, and the integral evaluation is really straightforward. All right, so we can picture this graphically if we draw what we call an indicator diagram. Okay, so you'll see this type of diagram pop up in a lot of textbooks or resources. All right, so it's really just an indicator diagram is really just looking at how your pressure changes with volume. Okay, so in the case of work done against a constant pressure, okay, let's say we just have this constant pressure. In the case of a lab experiment, that would be 1 atmosphere, atmospheric pressure. Okay, and then we're just asking ourselves what happens as our system changes volume. Okay, so we have some sort of change in volume, either an expansion or a compression. Okay, so if we start at V1 and expand to V2, okay, we can calculate the work of that expansion under this constant pressure, right, by just taking the area of that square, okay, or rectangle. All right, so just a straightforward integral, right, area under the curve, okay. So putting this in equation form, remember we have dW equals minus P dV, okay, so if we want to integrate that, okay, what's important to note here is that, remember, our pressure here is constant. So if that's constant, we can bring that outside of our integral. We end up with work equals minus PEX times the integral of dV from V initial to V final. Okay, we can simplify that as minus P times V final minus V initial, also known as minus P delta V. Okay, so for work done against a constant pressure, we have this nice straightforward calculation. All right, things get a little bit more fun when we look at the example of a reversible isothermal expansion of an ideal gas. Okay, so when an ideal gas undergoes a reversible isothermal expansion, the constant temperature is enforced by permitting heat to go into and out of the system. Okay, so we don't have an isolated system right now. We keep that constant temperature by allowing heat to either go out of or into our system to maintain that constant temperature. All right, so remember here, our keyword isothermal means we have delta T equals 0. Okay, always write down what you know. Extract these little pieces of information from your problem, from the information that you're given. Okay, it really helps you to start setting up the correct equation that you want to use for your calculations. Okay, so remember we have a reversible process. Okay, so changes are going to be infinitesimal and continuous. Okay, so in this type of process, we want to keep in mind that our pressure is no longer constant and depends on the volume change. Okay, so if you think about this as your gas expands, the volume of the system increases, which results in a decrease in the system pressure. Okay, and we can picture that with this indicator diagram. So again, we've got pressure as a function of volume. Okay, again, we are expanding. We have V1 expanding to V2. Okay, in this case, our pressure, where last time we had it constant going all the way across, in this case, we have a non-constant external pressure. Okay, so as that volume changes, our pressure is going to change as well. So as we increase our volume, you can picture that we're going to have a corresponding decrease in the pressure of our system. Okay, so we need a slightly new equation for work that accounts for the pressure dependence on volume. Okay, so we start out with the same equation. Okay, so remember, work is always defined as minus PEX dV, I should say dW. Okay, and now we just said that we know that this pressure is not constant and depends on volume. Okay, so maybe think about whether there's a way that you could express pressure, okay, in a way that allows you to see how it might respond to changes in volume. Is there an equation for an ideal gas that might tell you how pressure relates to volume? Hopefully you're screaming at me, piv nert, right? So don't forget what you know. Okay, so PV equals nRT. Okay, so knowing this relationship, again, remember ideal gas, right, gives us power here. So we know that pressure can also be described by nRT over V. Okay, so this allows us to get a sense of how our pressure is going to be affected by changes in volume. Okay, so this is how we get around not having a constant pressure. Okay, but we have a nice expression that allows us to model that in. Okay, so plug that into your expression for work, and we get minus the integral of nRT over V dV from V initial to V final. Oh, and we'll integrate dW. Okay, and then you can pull out all your constants. You end up with work equals minus nRT natural log V final over V initial. Okay, so we have a new expression now that allows us to easily calculate the work associated with a reversible isothermal expansion of an ideal. Okay, so hopefully you're starting to see that you can essentially derive these types of expressions from the same point. Okay, so we're always starting with the same starting point for our expression for work, okay, minus P dV. Okay, you just have to ask yourself what's going on with P. Okay, is it constant? Is it changing? How is it changing? Okay, so in this case, we know that pressure is changing with volume. Okay, so that allows us to set up our integral with respect to this change in volume. Okay, so next up is a reversible adiabatic expansion of an ideal gas. Okay, so in adiabatic processes, since there's no exchange of heat between the system and the surroundings, okay, so remember Q equals 0 for adiabatic processes, we know that the temperature is not constant anymore. Okay, we don't have that ability to exchange heat with our surroundings to maintain our constant temperature like we were able to do for our isothermal process. Okay, so now we have to consider the temperature dependence of work. Okay, so taking a look at our indicator diagram for this process, again, pressure is a function of volume. Okay, as we change that pressure, okay, we're also changing the temperature, okay, because we can't release that heat. All right, so just to make sense of this diagram for you, this line right here is what we would call our isotherm. Okay, that's how your pressure, you would expect your pressure to change for an isothermal process. Okay, so what you see for an adiabatic process is that you get some sort of delta T. Okay, so our temperature is not constant. So anytime you see these lines drawn on your indicator diagram like that, those all indicate some different temperature. Okay, that's occurring. Okay, so let's extract some information about our adiabatic process here. So we know that we have Q equals 0, okay, and we know that our temperature is changing, okay, we know that also our pressure is changing, okay, and our volume is changing. So a lot of things are changing here. Okay, so let's take a step back and remind ourselves that we know a little something about the relationship between work and heat and our internal energy, and we're going to use that to help us out here to get our expression for work for an adiabatic process. Okay, so remember, delta U is equal to Q plus W. Okay, always and forever definition of delta U. That's our first law. Okay, so we know that for an adiabatic process, that Q is 0. Okay, so delta U is essentially just work, right? And we've already said we know how to model work. Again, some things never change here. Work is always described for these situations, for PV situations, as minus P EX dV, okay, external pressure times dV. All right, and then we know that we can model if our pressure is not constant. Okay, we've already said that we can model that as minus nRT over V times dV. Okay, all right, so this is all stuff that we know. So none of this is new. Okay, we've already seen most of this already. Okay, we've got an expression for work now that takes into account our change in volume and the fact that our pressure is not constant. Okay, what we haven't done yet is to account for the fact that our temperature is not constant. Okay, so we need to have a way to account for the non-constant temperature in this expression. So the next thing we're going to do is to remember other things that we know about internal energy that might help us out at this point. Okay, so thinking back to our introduction to internal energy, remember that you know for an ideal gas, delta U equals CV dt, right? Again, explicitly for an ideal gas. Okay, so can we use that to help us get information about the temperature dependence of work? Yeah, because now we have two equations, right, for the same quantity. So we have one expression for delta U, right, in terms of our changes in volume, and we have another expression for delta U in terms of changes in our temperature. Okay, so let's put these together and see what we end up with. So we know that CV dt should be equal to minus nRT dV over V. Okay, so hopefully you're seeing that we can do just a little minor rearrangement here to get all of our variables that are changing on corresponding sides. Okay, so you can end up with, we've got CV dt over nRT on the left-hand side, and then that leaves you with minus dV over V on the right-hand side. Okay. So hopefully this is screaming out to you, hey, I can integrate this side with respect to T and this side with respect to V, and then end up with my answer. Okay, so what this equation gives you the power to do is you can calculate relative percent changes in temperature for relative percent changes in volume. Okay, so you're essentially getting the corresponding temperature and volume changes for a reversible adiabatic compression or expansion of an ideal gas. Okay, so again, you can use this equation to calculate, to calculate relative percent changes in temperature for a given percent change in volume, or you can integrate it to get the absolute temperatures or volumes associated with your reversible adiabatic compression or expansion of an ideal gas. Okay, so the real fun that we can do with all of these different kinds of processes is to put them all together into a cycle. Okay, so we can perform a series of isothermal and adiabatic expansions and compressions to create a cycle that starts and ends at the same state. Okay, so essentially what you have there is delta U equals 0. Okay, so this is the basis of heat engines and heat pumps, okay, which we have a lot of use for in our everyday lives. Okay, if you've ever used a refrigerator or heated your house or driven a car, okay, you have a reliance on these cyclic processes. So, when you want to account for the overall internal energy, work, or heat of a cyclic process, all you have to do is to take them step by step, like we just did. So, for this example process here, this is actually a Carnot cycle that you're going to play around with in your CGI. We have a hot isothermal expansion for leg 1 of our cycle, this red line. Next, we have an adiabatic expansion, okay, as our second leg. Our third leg is a cold isothermal compression. So again, volume's getting smaller, we're compressing, and then we finish it off with another adiabatic compression. Okay, so the right-hand side here, these are both expansions, and going on the left-hand side back up, those are both compressions. Okay, so put them all together and you get your full Carnot cycle, okay, which is essentially an ideal heat engine. Okay, so you now have the skills to calculate each individual leg, the heat, the work, the delta U for each individual leg of a cycle like this. Okay, so then you add them all up and you get your final values for work and heat associated with the cyclic process. So whether you want to produce heat or consume heat, whether you want to heat something or cool something, okay, you can design your cycle to go in such a way that you produce the process that you want. All right, I hope that's helpful. Thanks.